Good afternoon, everyone. My name is Timothy Buttsworth. On behalf of myself, as well as my co-organisers Paul, Brian and Glenn Wheeler, I'd like to express my gratitude for you all coming along to this seminar. We're quite excited to do some maths with you this semester. So the point of this seminar series is really to give an opportunity to our community of geometers, both academics and students from around Australia, give them an opportunity to come together, have a bit of a forum, and ultimately to learn some interesting pieces of mathematics. Most of us who are in attendance, I believe, are from Australia, and so given how this is our first seminar of the series this year, I think it'd be good to take a brief pause to reflect on how lucky we are to live in this country, Australia. I think it's certainly one of the most beautiful countries I've ever seen, and so perhaps it's good to take time to acknowledge the traditional owners of this land, to express. I in particular would like to express my gratitude to the traditional owners of this land, both for their ongoing custodianship of this beautiful country as well as their ongoing cultural contributions. Of course, we like to encourage international participation where such things are possible. I know that some people like to, well, not from Australia because this isn't the right time in other countries, but other international people like watching these seminars on YouTube later. And so if this is you, welcome as well. Okay, so on to the mathematics and the seminar details. We're into our fourth season of the Australian Geometric PDE seminar series so far. So I'd like to thank you all for your attendance, ongoing attendance at these things. By popular demand, the topic that we chose for our fourth season was the mean curvature flow with surgery. So at this point, I'll point out that our goal is to learn about the mean curvature flow with surgery. And I say the word learn in as much underline and bold as I possibly can, because ultimately this seminar series is directed for PhD students. Now, this is a learning seminar, and we want to, as much as we can, give an opportunity for PhD students and other research degree students to learn these things. And so I'd like to emphasize that in the large, this seminar series is by students and for students. The expert academics will, of course, be here as well, and we'll be looking forward to having their contributions in their various ways. But ultimately this seminar series is not for them, it's for the students. So what I would like is to encourage any students we have in attendance to, whenever you feel like you need some extra clarification on something, please feel free to make your concerns known. Certainly, the experts will probably know the answers to that and wouldn't need to ask such questions, but ultimately this seminar series is not for them. In the large, it is for the students. So please feel free to interrupt, ask questions, and mistakes will happen. This is all a learning process. We're here to learn together. All right, with all of that said, I'll point out that the majority of the students, the majority of the people that will be speaking in this seminar will be students. So without further ado, I'd like to introduce you to our first speaker for this series, Marcus Flook. Marcus Flook is currently at ANU. He used to actually be a student of mine, but now he's gone on to greener pastures at ANU with Ben Andrews. And so Marcus is going to give us an introduction. Remember, ultimately, we want to talk about mean curvature flow with surgery, but of course, it'd be good to start with the basics, mean curvature and mean curvature flow. So I'll hand it over to you, Marcus. Thanks very much.
Thank you very much for the introduction, Tim, and thank you to Tim, Paul, and Glenn for organising this seminar. I'm very much looking forward to participating. So hopefully, just to give a quick motivation for this problem, we say that a minimal surface is a surface which locally minimizes its area. And such surfaces appear ubiquitously in nature. Possibly the most famous example of this is from soap films. So we can see an example here of a catenoid, a minimal surface, being formed by this soap film. Now, a characterization that's going to be very useful for us moving forward is that minimal surfaces have a mean curvature of 0 everywhere. Now, whoops, sorry about that. Now, we say that a surface evolving in such a way as to decrease its area most efficiently is said to evolve by mean curvature flow. Now, we're obviously going to flesh out exactly what we mean by that precisely. But to give a very quick intuition, if we take this idea of a sphere, using the image from Ecker, we can see that a sphere is going to reduce its area by obviously shrinking. I'll quickly look in the chat. Someone shout out if there's
no, it's all good. It's all good.
Perfect.
I was just checking if it appears okay for people. Yeah.
Now, the evolution of these surfaces satisfies what we can think of as a geometric heat flow. So looking at this slide, two of the things that I hope we can really come away from is that what do we mean by decreasing the area most efficiently, and what do I mean by a geometric heat flow? So Tim asked me to give a quick recap of the geometry of embedded hypersurfaces in Rn+1, which I'm very excited to go through. What I would note is that for a more detailed explanation, I'd highly recommend seeing Appendix A from Regularity Theory of Mean Curvature Flow by Klaus Ecker. I'm predominantly going to be using the notation from there. Okay, so suppose we have an n-dimensional manifold. We say that a differentiable map is an immersion if for any point on the manifold, the derivative map between the respective tangent spaces is injective, obviously for all x on that manifold. If this map maps homeomorphically onto its image in Rn+1, then we say that f is called an embedding. Now, for the majority of this talk, I'm probably going to be restricting myself to talking about embeddings. However, we can define a broader theory that includes looking at the immersion. When we're saying an embedding, I'm realistically just trying to exclude surfaces like self-intersecting surfaces, making the conversation a bit easier. Okay, so the coordinate tangent vectors defined here as partial I of what we have here, the embedding map being defined from the coordinate vectors of the original manifold, are going to form a basis of the tangent space. So here we have the tangent space of the hypersurface at the point defined by where the embedding is placing it. So we have the embedding, and the embedding will allow us to define a basis for the coordinate tangent vectors, or rather a basis of the tangent space. Okay, so suppose that we have an embedding and that we call the calligraphic M the embedding, well, where the image of this embedding. Then we can define the induced metric on this hypersurface by the Euclidean dot product of the spatial derivatives of our embedding. So where I have the dot product here, I'm talking about the Euclidean dot product in Rn+1, inherited from the ambient space. Now, of course, when we have our induced metric, we can define the inverse metric. Notice here that I'll be using notation where we often refer to as Einstein summation notation. So what we'll be doing is summing over the repeated indices. So what we're saying here is that the inverse metric, Gij, summing over the j's with Gjk is equal to the Kronecker delta. And we define the area element by the square root of the determinant of our induced metric. So this will allow us to do things like integrate on a hypersurface. Okay, so suppose we have some function which is going from our hypersurface into the real numbers. Via the embedding map, we can actually think of this as a function on the original manifold. And in doing so, we define the tangential gradient of this function by the trace of the partial derivatives of f and the embedding itself. So what we can notice is that this is indeed the tangential gradient because we're getting a linear combination of the derivatives with respect to the tangent, the basis that we have for our tangent space at any point. In the same way, we'll define the Laplace-Beltrami operator of some function with a bit more complicated definition. Here we're taking the trace of the second spatial derivatives of our function minus this term of the Christoffel symbols summing with single derivatives of the function here. And the Christoffel symbols are given by, in our case, we can define them as just the tangential component of the second derivative of our embedding. Okay, so we're working with an embedded hypersurface. Let nu be a choice of our unit normal vector field. In particular, one thing that would be particularly useful when we're doing computations is just to make sure that whilst it is obvious that the normal vector field is always going to be orthogonal to the tangent vectors on our tangent space at all points. Where it makes sense, the convention that we're going to follow is we're going to take nu to be the outward pointing normal vector. This is a bit, depending on where you're reading from, this can be taken as either the outward or the inward. We'll be using the outward from Ecker. And it should be noted that the spatial derivatives of our unit normal field are going to be tangent to this hypersurface. For a quick computational verification that we should become very familiar with, if we take the spatial derivative of the norm squared of the unit normal field, that's of course going to be 1. So that's going to be 0. But of course, when we actually expand this out, we see that partial I dot product with the normal vector is going to be 0. Okay, so we define the second fundamental form of our hypersurface as the Euclidean dot product of the derivative, the spatial derivative of our unit normal vector field with the spatial derivatives of the embedding. Note that we can also consider this in this form, where all we've done is taking one of the derivatives out. This then necessarily has to be 0. And so we can use the product rule to show that this equality has to hold. That's a quick verification if anyone wants to do it. And we'll use both forms depending on which computation is easier at the time. So it's worth having both. Now, the mean curvature of our hypersurface is going to be given in our case by the sum of the principal curvatures, which we can think of as the trace of the second fundamental form. I say in our case because there are some authors that again use a different convention of taking the mean curvature to be the average of the principal curvatures. But again, we're following the convention given in Ecker. Just to give a quick recap so that people who are a bit unfamiliar with the principal curvatures, if we think about, say, looking at the sphere S2 with some radius, say R, then in this case, the principal curvatures are both going to be 1 on the radius. So in that case, we would have the mean curvature would be 2 on R in that case. 2 examples that's very good to familiarize yourself, at least for working with a lot of the initial examples, is with a round cylinder and a sphere of certain radius. Okay, so we finally have the tools to define the mean curvature flow. So suppose we have a smooth 1-parameter family of embeddings into Rn plus 1. This satisfies mean curvature flow if the time evolution of the embedding evolves in the direction of the normal vector with speed governed by the mean curvature. So in the case of the sphere, where we have some positive mean curvature and an outward pointing normal vector, we can see that that sphere is going to indeed shrink. So that gives us a nice little idea of what we can think about. But note that the speed of the flow is governed by the mean curvature. And in what follows, whenever we have the calligraphic M, that's going to denote the embedded hypersurface, whereas the normal M is the original manifold. Okay, so I promised an example, so let's have a look at the sphere. So suppose we have the N sphere of some positive radius centered at the origin. And let's just have our standard embedding, where we start with a radius of rho, say, for example. Now, looking for a solution to mean curvature flow, we have that the mean curvature is the same at all points. The normal vector is going to be pointing in the same direction as where the embedding is placing us. So it's reasonable that when we're looking for a solution, we can make the ansatz, we can make the assumption or expectation that the solution remains round. So what we're going to do is we're going to assume that the solution is of the form here, where all that changes over time is the radius of our sphere. So we're going to parameterize the sphere with the following embeddings. We're going to take a map from, so the initial manifold here is the unit sphere, the unit N sphere, I should say, embedded into Rn+1, defined as follows. So we're taking a point on the on the unit N sphere and mapping that to some point where we have the radius component, but again, the spherical component. So this is just going to give us a sphere of radius r. Now, what we should realize, hopefully pretty quickly, is that the normal vector is then given by this position on the unit circle, and the mean curvature, from what we were saying before, is at every point n divided by the radius. So when we substitute this into the mean curvature flow equation, what we see is that the evolution of the embedding, which in our case, when we actually do the computations, is the derivative of the radius function, is equal to minus n over RT, again with that position on the unit sphere. So if we then look at this as an ODE, we can say that the embedding satisfies mean curvature flow if and only if the radius, or rather the derivative of the radius, satisfies this ODE, or the radius satisfies this ODE, I should say. Now, this is very quick to solve. This gives us an initial value problem with initial condition given here, where the radius at time 0 will be rho. And the solution of this is given by this equation here. So I guess a quick exercise for those at home, brush up on your ODEs, make sure that you can solve this and get this as your solution. So the radius is going to be decreasing with the initial condition there of the rho squared, or rho rather. Okay, so the shrinking sphere, which is the family of embeddings defined as follows, is going to give us a solution of the mean curvature flow. And also, Eka gives us a very nice visualization of this, where what happens is the sphere will start to shrink until eventually it develops a singularity at finite time here. So we can see that we can't evolve this past the final time that we have here, rho squared over 2n. And in fact, this is actually what we would call an ancient solution, meaning that we can extend this solution all the way back, and it's defined on this interval here. A quick similar example, which we'll go through probably a bit quicker, is suppose we have some kind of cylindrical initial condition this time. So we have the n minus m sphere of radius rho with Cartesian product with Rm, again for some positive radius. And as before, it's reasonable to assume that a cylindrical solution remains cylindrical. And so we're going to search for a solution of the following form here. Now, in this case, the embedding it's a bit tricky, but still nothing that we have to really work too hard for. In this case, this is our initial manifold. And we're going to be defining these family of embeddings by taking a point on the n minus m unit sphere, multiplying that by this radius function, and then keeping this y term the same. Now, in this case, the normal vector is, again, it's going to be time independent, and it will only depend on the x coordinate. And the mean curvature, note that now it's still going to be the same at all points, but notice that it's n minus m now. That's because we still have the n minus m principal curvatures of 1 on RT from the sphere, but the principal curvatures of that Rm component are going to be 0. That's a bit hand wavy and there's a bit more work to it, but hopefully that's satisfactory. Okay, substituting this into the mean curvature flow equation, we're going to arrive at a very similar ODE. We can see here that it's going to satisfy mean curvature flow if and only if we satisfy this ODE, which has the explicit solution with initial condition governed here. So in this case, we have another class of solutions, say, which are governed by the shrinking cylinder. Again, defined with a finite time. Note that this is as well an ancient solution, in which case we can extend it as far back as we would like. Again, thanks to class Ecker for the images. Now, more generally, suppose we have a solution to mean curvature flow in R n minus m plus 1, then the family of product hypersurfaces, so this is exactly what we did with the spherical example, will also be a solution to mean curvature flow in Rn plus 1. One reason this is particularly nice is because if we take n equals 2 and m equals 1, we can immediately get that all of the solutions to curve shortening flow will create cylindrical solutions in higher dimensions. So to gain some kind of intuition, it's actually nice that we can play around with curve shortening flow and then see that in the cylindrical case, they will evolve in the same way, obviously with the real component as they're giving it the cylindrical shape. Okay, so as Tim mentioned, we're going to be talking about mean curvature flow with surgery. And unfortunately, at this point, I want to give an example to motivate this idea of surgery. So the singularities that we've seen so far, it isn't obvious in a sense that we can evolve past those singularities. In fact, in both cases, the mean curvature at all points flies off to infinity. So what I want to try and give now is a very classical example where we develop a singularity in finite time. But to do so, I'm going to have to be a bit cheeky and state 2 theorems without proof. However, once we've done a bit more of work on mean curvature flow, we will go back and actually prove these. So the first result, commonly called the comparison principle, states that any 2 smooth compact solutions of mean curvature flow, which are initially disjoint, stay disjoint. We could see this already explicitly with the sphere in the case of where we could parameterize, say, terrible drawings, unfortunately, but if we can bear with me, if we imagine that these are spheres, then based on the equations that governed them that we had previously, we could tell that they were always going to be disjoint. More interesting examples, you can already see things like, say, this case here, where we have the some more interesting hypersurface here contained entirely in our sphere. Now, what this means is that this is going to have to either converge to a point in a similar way, or in some sense, it's going to lose its smoothness in finite time. But we want to give a more concrete example. And for that, we have a nice results presented in Ecker. I might try and, there we go. And that's called the hyperboloid/cone comparison. So bear with me if this seems a bit blocky at the moment. It'll become a fair bit nicer. So suppose we have a solution of mean curvature flow. Let x be the point in Rn plus 1, so that x tilde is the first n coordinates. Now, if we have some beta bigger than or equal to 0, less than or equal to n, and some epsilon bigger than 0, if the initial hypersurface is contained inside this hyperboloid, then the evolution of this hypersurface under mean curvature flow has to remain inside this evolution here. Notice that at some finite time, this becomes a cone. So this will exist for t less than epsilon squared over 2b. Now, to give a nice visualization of this, let's go to the image from Ecker. Now look at, so these lines here are what we're getting from the hyperboloid. And as we can see, in finite time, based on the evolution described here, this is going to just form a cone. So with this dumbbell hypersurface here, we can hope to find some kind of singularity development at the neck. Now, the reason we also have to use this comparison principle here is because if this was all we had, we wouldn't have a guarantee that, say, this side, if we imagine that it was smaller than this side, without this principle, the comparison principle, there's no guarantee that, say, this doesn't evolve through the cone before that singularity develops. So what we do, now that we have some finite time where the cone forms, if we create the dumbbell so that in its interior of both of these sides here, we have sufficiently large spheres, then we can guarantee that both of the dumbbell sides will exist after this finite time. So making the argument a bit more rigorous, as I'm sure we'll do as we move on. But in our case, using both of these principles, it's sufficient to show that we have a singularity here. What I should note as well is that this is the first example of where we find a singularity where intuitively we're left wanting to continue to evolve both sides. So for example, what if this were to evolve, it's going to look something like this. So whereas in the previous examples, we had the mean curvature everywhere was flying off to infinity, it seems as though there should be some way in which we could have surgery to continue the process on these two sections that remain here. So, this is a very nice example to try and indicate some of the behavior that we're interested in.
Sorry, can I get a quick question?
Yes.
So the avoidance principle you mentioned, it is also true for non-compact hypersurfaces?
This principle here?
Yep.
Yeah, so I believe in the strongest way that you can frame the theorem that I'm familiar with, one of them has to be smooth compact, but the other need not be.
Okay, so at least one of them should be compact. Okay, I see.
Yes, so in this case, so in the form that I'm stating it here is probably in a weaker state than we can prove it for, but it's sufficient to demonstrate the singularity here. Note, because whilst this is obviously non-compact, the smooth compact solutions that I'm talking about are the dumbbell and the spheres. Hopefully that answers the question.
Yeah, but I think if you want to say it also develops the singularity at a time, you also need to compare the dumbbell with that hyperboloid, right? Is it the point?
Yeah, so the dumbbell is being compared to this hyperboloid here.
Yeah. So then for this part, you need like a stronger statement you mentioned just now, right?
Yeah, so we can prove a statement like this using a version of the weak maximum principle.
Okay.
So yeah, we'll get to that. It's a bit hand wavy that I have to state these without proof, but
okay, yeah, that makes sense. Yeah, thanks.
Thanks so much for the question. Okay, so let's have a look at this as a PDE. Suppose we have a solution to the mean curvature flow, and suppose we have a diffeomorphism of our manifold, just mapping from the manifold into itself. then if we have the composition of the embedding with the diffeomorphism, this is also going to be a solution. So this is indicative of the fact that the curvature flow depends only on the geometry of the hypersurface, not how it's parameterized. And it also, very importantly, implies a degeneracy in the tangential directions of our problem. But we will flesh out exactly what I mean by that in a bit. So if you remember at the start of the talk, I said that we can view mean curvature flow as a geometric heat flow. Let's now make that a bit more rigorous. So suppose we have an embedding going from some manifold to Rn plus 1. Then the Laplace-Beltrami of the embedding is equal to minus the mean curvature times the normal vector field. Notice then the mean curvature flow equation is in this form, which is much more, it very clearly resembles your traditional linear heat flow. Now, what I want to do for the next little bit is actually show that this is the case. So this is both a good exercise just to make sure that we can actually verify this is the case, but it also makes quite evident the degeneracy that I was talking about before. So in the way that we defined the Laplace-Beltrami, it will be acting on a function defined on our manifold. So in our case, we're going to be looking at this case here, where we're looking at the EM component of the embedding. Now, by definition, this is taking the trace of the spatial derivatives with this embedding term minus the Christoffel terms, again, with the derivative. Now, notice that if we pass these into the inner product, taking the spatial derivative of the basis vectors is going to be 0. So we can just pass them through here. Now, remember the way that we discussed the Christoffel symbols was this Christoffel symbol with the repeated sums with the spatial derivatives of the embedding is equal to the tangential component of partial I partial j x. Now, what this means is that if we have some quantity minus the component that's tangential, but of course we're left with the normal component. Now, in our case, this is equivalent to saying, okay, let's have the dot product with the normal vector, as we do here. And what we should notice, although it might be a bit unclear at first, that this was exactly the expression we had for the second fundamental form. So using that expression here, we have the trace of the second fundamental form. That's precisely the mean curvature. Now, when I was saying it makes evident the degeneracy in the tangential directions, notice that in here we're exclusively talking about the normal component of the second spatial derivatives of the immersion. This is what we mean by it has a degeneracy in the tangential directions. And so we have a weakly parabolic PDE. And this directly corresponds with the diffeomorphism invariance of the mean curvature flow. And this weakly parabolic is probably the first stumbling block that we should really take time to consider, because if we had a strictly parabolic PDE, then we would be able to much more easily make use of standard PDE theory. So this is the first stumbling block that we have to try and deal with. Now, one example that I didn't talk about before, but is nice to think about, is what we call a graphical hypersurface. And these are just the graph of some function. So in our case, let's let the embedding be the graph of some smooth function u. Note that this is, again, a strengthened condition. We could loosen this requirement on the smoothness of u and still have the mean curvature flow make sense. But for our purposes, let's stick with a smooth u. Now, in this case, and this is maybe an exercise that I'll leave for people to look at. In this case, the graphical hypersurface satisfies mean curvature flow if and only if the u function satisfies this PDE. So the derivative of u, the time derivative of u is equal to the square root of 1 plus the gradient of u squared times the divergence of the gradient of u divided by the square root of 1 plus grad of u squared. Now note that this PDE is quasi-linear and it's strictly parabolic. So the moral of this, which is a tool that we'll keep coming back to, is that if we consider a hypersurface locally as the graph of a function, we can break the diffeomorphism invariance of the mean curvature flow, meaning mainly that we break this idea of the weak parabolic nature and we can get to a strictly parabolic. This will be, there are various ways of proving things like short-time existence. In a lot of them, this is a key technique. Okay, so we've talked at the moment about how this is a geometric heat flow. One thing that hopefully should be a natural question for people is we're saying that this family of embeddings is evolving by some geometric flow. And as hopefully you understand from geometry or recall from the recap, is that when we were defining the quantities like our metric, area, element, second fundamental form, mean curvature, these all depended on the embedding. So if the embedding is going to evolve, we need to understand how the corresponding geometric quantities of the hypersurfaces are going to be evolving. So for example, what can we say about the mean curvature of a surface? We saw that with the sphere, as the sphere underwent mean curvature flow, the mean curvature flew off to infinity. So what we want to try and understand is what evolution equations govern the evolution of these geometric quantities. Easiest way to start off with is let's just have a look at the evolution of the induced metric. Now, a very quick application of the product rule. You can do things a bit quicker, realizing the symmetry of Gij. But if you want to go through the brute computation, all we're doing here is applying the product rule. In the next step, all we're doing is recognizing that this is a family of embeddings, which is undergoing mean curvature flow. So we're just using that mean curvature equation. Now, again, just a very simple application of the product rule. What we should notice here is that we're taking the Euclidean dot product with respect to these tangent vectors. And so when we have, say, the derivative of the mean curvature times the normal vector, these are going to vanish. So all we're going to be left with is minus 2h, the inner product of the spatial derivative of the normal vector field and the spatial derivative of the immersion, the embedding rather, and that's precisely minus 2h, the second fundamental form. So we have a nice understanding of how the metric evolves. So again, suppose that we're just working with some solution to mean curvature flow. So what we want to do here is compute the time evolution of the area element. Now, hopefully people have seen this equation before, or this statement before, where we have the time derivative of the determinant of some matrix. In this case, a metric is equal to the determinant times the trace with respect to that metric of the derivative. Hopefully people have seen some version of this result in linear algebra. What we want to compute is how this area element evolves over time. So taking the time derivative, we can see that we're left with 1/2 the square root of the determinant of the metric with the derivative of this determinant. Using our result up here, we see that we just get this factor here. Obviously, these will cancel out, giving us the following. Now, the trace of the time derivative of g, from the previous slides, we saw that the metric evolves by minus 2h, the second fundamental form. Here, we're taking, again, the trace of the fundamental form. So what we're going to be left with is minus the mean curvature squared, times the mean curvature squared times the square root of the determinant of the metric, that original form. So if we want to integrate over our manifold, we obviously need to look at the measure that we're integrating with respect to, that we inherit. And that's going to be expressed as follows. Now, once we have this, we can prove the following. So suppose that Mn is a closed manifold, and we're mapping from the manifold, and we have our family of embeddings which solve mean curvature flow. Then the derivative of the area of our hypersurface, which is equal to this quantity here, is minus the integral over this hypersurface h squared, which is less than or equal to 0. Note as well that it's only equal to 0 when we have a minimal surface. Regardless of whether we have positive or negative mean curvature, the area is still going to decrease. Now, with a bit more work and a bit more rigor, we can show that the mean curvature flow is the L2 gradient flow with the area functional. We might come back and prove this a bit more rigorously later in the seminar, but for now, this is the sense in which I mean that the area is decreasing most efficiently, because the mean curvature flow is the L2 gradient flow with the area functional. Another interesting property to think about is how does the normal vector evolve? Unfortunately, again, if we look at our examples that we've considered, they always had time-independent normal vectors. We looked at, say, the sphere and the cylinder solutions. The normal vector was always the same. So we want to try and get an idea of, okay, does that just mean that the normal vector remains the same? However, intuitively, we can understand that that's almost certainly not going to be the case. So let's try and figure out how the normal vector will evolve. To compute this, we're going to use tricks that we saw in the introduction section. If we recognize that taking the time derivative of the norm of v squared is 0, then we can see that here the inner product of the time derivative of the normal vector field is going to be orthogonal. And so this is going to be tangent. In particular, this means that we can represent it as the following linear combination, taking the trace over these quantities. So now what we want to do is to figure out what the time evolution of partial t v is. We want to understand exactly what these coefficients are, because at the moment we don't have a very good understanding yet. So what we should note, again, we're doing the trick in trying to take the derivatives out of the inner product to try and see what's happening inside. Inside of this time derivative of the product of the outer normal and the unit vector field Euclidean dot product with the spatial derivative of the immersion, this has to be 0. Quick application of the product rule tells us that if we apply it here, that we're left with these two quantities. This quantity being the one that we want to compute, this quantity here being one that hopefully, with some work, we can get into a more amenable form. So if we work this through, again, we just take, again, product rule, then we can see that we're left with these two quantities here. Here we're taking the Euclidean dot product of the normal vector with the spatial derivatives of the normal. This is, of course, just going to be 0. And so we're left with this quantity that we wanted to find is equal to the spatial derivative of the mean curvature. Now, if we substitute that back into this expression here, what we find is that we obtain precisely the statement for the tangential gradient. And this is really nice because we're saying that suppose you have a hypersurface which is evolving via mean curvature flow, then the normal vector is going to evolve in the direction of the tangential gradient of our mean curvature. We should note as well that this aligns with the situations that we've already looked at. So if we look at the sphere, we look at the cylinder, these had constant mean curvature. So in this case, the tangential gradient was always going to be 0. The normal vector won't spatially evolve, won't evolve in time, and so it's going to remain where it was. So this completely aligns with what we've seen, even though the examples that we saw were quite small toy examples. So in the next quantities that we're going to be looking at, the main thing that I want us to be thinking about is, okay, how does the mean curvature evolve? And in one way of looking at that, we want to look at the time derivative of the trace of the second fundamental form, which means we want to find how does the inverse metric evolve, but also how does the second fundamental form evolve as well. Once we have those two pieces of information, we can combine them and see how the mean curvature evolves. So first, let's have a look at this inverse metric. What we should notice is that, again, just by the strict definition that we have here, Gij summing over the repeated indices, this is going to be particularly useful for us because if we take the time derivative of this, well, it's not going to change. So in this case, the derivative of this quantity has to be 0, which is fantastic for us because we can then use the product rule as we've become accustomed to at this point. So we have the time evolution of the inverse metric plus the inverse metric evolution of the metric. Now, the evolution of the metric is, of course, just minus 2 the mean curvature and the fundamental form. Now, this inverse metric is going to contract, giving us this term here. Now, obviously, because we have the 0 here, we obtain this particularly nice expression, which is getting us closer to how this term in particular will evolve. Now, if we want to contract again, because we want to isolate for this term here, so we have to get rid of this metric term, contracting using this inverse metric here, we're left with the following statement, which means the time evolution of the inverse metric is given as follows. Computing the evolution of the second fundamental form is probably the next most arduous component that we have to get through. So we'll try and get to this. Hopefully the evolution of this will be a nice place to end. So to compute the time evolution of this second fundamental form, it will be very convenient to work in geodesic normal coordinates, such that the metric is given again by this Kronecker delta expression, and the tangential components of the second spatial derivatives of the embedding are 0. Now, in this case, we can just look straight up at what the time evolution of the second fundamental form is, just by definition. Again, applying the product rule. Now, if we look at this first term here, note that for partial I, partial j of x, we've said that because we're working in geodesic normal coordinates, the tangential component of this is going to be 0. So this is acting in a normal direction. But we know from the previous computations that we've done that the time derivative of our normal is going to be tangent. So the dot product of this is going to be 0. These are always going to be orthogonal to each other, working within this coordinate system. And so we're left exclusively with this term here, where we've passed the time derivative through the spatial derivatives and applied the mean curvature flow equation. Next step is just, again, applying the product rule multiple times. Note now that these middle terms here will vanish because we have the spatial derivatives of the normal vector with the normal vector, and we're left with these terms here, mainly because the norm of the normal vector square is going to be 1. Now, if we take one of those derivatives out, what we're going to notice again is that the normal term is orthogonal to the tangential term. And so using the product rule, as we have a few times now, we're able to get to this expression here. So as we've done before, recognize that this quantity of the spatial derivative of our normal vector field is going to be tangent. And so we can express it in the following way, which means, again, contracting on that second fundamental form, we can arrive at that expression. When we substitute that in, that's particularly nice because what we notice is that this remaining term here, which is the inner product that remains, is just going to be, by definition, the second fundamental form. And then recalling that we're working in geodesic normal coordinates, we obtain that the time evolution is equal to these tangential gradients of h minus h, these components of the second fundamental form, and a contraction. Now, where I wanted to get up to by the end of this talk is looking at the evolution of the mean curvature. So again, recall that the mean curvature is the trace of our second fundamental form. Applying the product rule again, we're going to see that we want to substitute in these terms here. Recall that from the evolution of the inverse metric, we had that was the contraction of our second fundamental form, meaning that this component gives us 2 times the mean curvature times the norm of the second fundamental form squared, plus the trace of the time evolution that we previously computed. Now, looking at the trace of this final term back here, what we're going to see is that this will be minus h, again, the norm of the second fundamental form squared. So one of these terms here is going to be knocked off, and that the trace of this quantity here is exactly the Laplace Beltrami. So we're left with this expression here for the evolution of the mean curvature. Which is fantastic because we now end up with this equation here. This is probably a good place to stop, just because we've got 5 minutes left until the hour. So what we will, well, one of the primary things that we want to do in the next session is considering under what conditions can mean convexity be conserved? Or more importantly, showing that if, or more accurately, I should say, if we start with a hypersurface which has positive mean curvature flow everywhere, we want to show that that is indeed conserved. It's going to remain for the entire time. So that would be a nice use of standard PDE theory to get a very nice geometric interpretation of the flow. I'll call it there. Thank you very much for listening. I'll hand it over. Yeah, I think Ben was going to give us an indication of where the talk, where the seminar series will be heading.
Right, maybe first, sorry, Ben, maybe first we'll just
go on,
thank,
yeah.
maybe we should
Yeah,
thank
right.
Marcus.
Thanks, Mark. Yeah. Nicely done.
Yes. Yeah, thanks a lot, Marcus. I know from experience that writing evolution equations for geometric evolution equations is probably one of the most important things, but also maybe one of the least fun things that you can do. So thanks very much for doing all of that for us. I'll now hand it over to Ben, who I think has some comments about where we're going with the rest of this seminar.
Okay, thanks, Tim. Yeah, so Marcus suggested it would be nice to have some kind of a picture of where we're heading as a sort of overall goal of the series. So I'll try and give a very brief rundown of that. Although, to be honest, I mean, really the main point is just to work through at a nice, easy pace, and that was perfect what you did just there, Marcus. I think that will be, going through the details like that is a really good idea. So the rough outline of where the talks will head. I think that maybe the next talk, or maybe the next two talks, might be on sort of basic properties of the mean curvature flow, such as we'll see, as Marcus indicated, the consequences of the evolution equations we've just defined, which would be things like showing that mean convex hypersurfaces stay mean convex, or that convex hypersurfaces stay convex, that sort of thing. And also the fact that just like in the classical heat equation, the mean curvature flow tends to smooth things out. So we'll prove something along the lines of the statement that as long as the curvature stays bounded, then the solution remains smooth. So you automatically have control on all higher derivatives of the curvature and of the embedding. So those sort of things we'll look at first. Then I think the first main result we'll be heading for is Huysken's theorem on mean curvature flow for convex hypersurfaces. So that's the nice result that if you start with any closed convex hypersurface, that it will shrink to a point, and that it will become round in shape as it does so in finite time. But really, the longer term goal is to understand the sort of the picture that Marcus indicated of the neck pinching singularity there. So that, I mean, we should step back and be a little bit careful about what the example he went through showed. Okay, so what he proved was that something must go wrong, right? So you have these barrier arguments, you have the hyperbolon on the outside and the sort of the two big spheres which prevent it all from disappearing, which means that something must go wrong with the flow before everything disappears. You have to have a singularity without the thing shrinking to a point. And heuristically, we'd like to think that that means that you'll get a neck pinch in the middle, and then you could cut that neck pinch out and then continue with the two spheres somehow. That's the idea of the mean curvature flow surgery. To actually prove that takes a lot of work, and that's the sort of technical guts of what we'll have to work through, which will probably take quite a few talks to do that. There are several stages involved in that. The first stage is the result of Huysken and Singularities, which essentially proves that if you zoom in on a singularity where the mean curvature is going to infinity, that it looks almost convex, right? The hypersurface, essentially, when you blow up on that singularity, the hypersurfaces will become convex. That kind of gives us a good understanding of the behavior. And so that's the next sort of big stage, is the results of Huysken and Singularities about asymptotic convexity. That holds whenever you start with a hypersurface that has positive mean curvature. And then the last stage is the surgery part. So there, if we assume a stronger condition, which is so-called two convexity, you show that the only types of singularities that can arise are essentially shrinking spheres, as you get in the convex case, or cylinders, which should correspond to what we have in this neck pinch picture. Okay, and with good enough analysis of what the hypersurface looks like there, you can put this surgery program into place and construct a mean curvature flow with surgery, which sort of dissects that hypersurface into pieces that you can understand. Yeah, so that's the rough outline. And there's, well, maybe just to indicate also, there's a bit of a difference between the case of two-dimensional surfaces in three-dimensional space and the higher dimensional picture. So the higher dimensions, where the hypersurfaces dimension at least 3 were dealt with by Huysken and Singularities in their surgery paper. But then the two-dimensional case, even though it's lower dimensional, turns out to be harder, and that was dealt with much more recently by Brendler and Huysken. So ideally, we'd get through that series of main results by the end. But I think we'll just play it by ear and see how far we do actually get.
Cool. Thanks very much for that outline, Ben. I'll now invite people to ask questions of Marcus regarding his talk, or to Ben even on where we're headed. Does anyone have any comments or questions at this point?
Maybe just a comment, Tim, and then so with the example with the hyperboloid, I guess an alternative might be to use an Unguent torus shrinking around the neck. That, I suppose, avoids worrying about comparing with a non-compact thing.
Yeah, actually, in that example, the comparison with a hyperboloid is not done by the avoidance principle for mean curvature flow. It's actually just done by applying the maximum principle on the evolving hypersurface to a scalar function. Right? Namely, in fact, this, I guess, Marcus, you got the previous page to that one. Yeah, this, the function there, which defines the MT, right? So there you can think about it as just a function on the evolving manifold, and you just apply a normal maximum principle to that. So there's no issue really for non-compactness of the hyperboloid itself. It's applying to a scalar function on a compact manifold. It is still nice to see the example of the torus, but on the other hand, it takes some time to go through the details of constructing that. So yeah, that would be a nice exercise for anyone who's interested to read the papers and understand that example.
Does anyone have any other questions or comments? All right, then, in the absence of any further comments or questions, let's thank Marcus again for his talk, and to Ben for giving us an outline for the rest of the semester. All right, thanks everyone. I'll stop recording in a second, and well, stay tuned. We'll give you more information about what's to come in due course. Thanks for attending, everyone.